So today we want to have a look at compound interest. So another example of exponential growth and decay. So following on from what we talked about yesterday, but a specific group of examples around compounding interest. So when you take out a loan, so if you were to go to the bank and take out a home loan or a car loan or whatever it might be, the bank would charge you interest. So they're going to give you a big lump sum of money so that you can buy the house, so that you can buy the car, whatever it might be. And as a payment for that, you will then pay them interest. So if they lend you, $20,000 to buy a car, you won't just pay them back $20,000, you will pay them back $20,000 with interest. So with some extra money, that is a fee, essentially, for them lending you that money up front. Obviously that process can work in reverse as well. So if you make an investment, you invest money into the bank, for example. So you put a large amount of money into a savings account, the bank will then pay you interest for the privilege of that, okay? The fact that they get to hold your money. So you put, $10,000 in an investment account and it will earn interest, so that amount will grow over time. Okay, so we want to have a look at a particular example, which is compound interest, which is actually, there's also simple interest, but compound interest is what happens in the real world. So compound interest means that the interest is calculated at each compounding period based on the balance of the loan or investment at that time. So for example, if we were to invest $10,000, which is actually what this first example here is, and the first example here is $10,000 invested with interest paid at a rate of 3% per annum. So per annum, meaning per year, okay, compounded annually. So that means once a year the interest gets compounded, okay. So that means that we invest our $10,000, after 1 year we increase the value of $10,000 by 3%. So remember we talked about increasing by 3%, okay? Yesterday we talked about this sort of thing. So 3% increase means that we're ending up with 103% of what we started with. Okay, so that means we're multiplying by 1.03 to increase by 3%. So at the end of 1 year, we're going to increase our 10,000 by 3%, so 10,000 times 1.03, and we get $10,300. Okay, so then compound interest, if it was simple interest, so we can see that the interest in the first year was $300. If it was simple interest, every year we would just add in $300, okay? But in compound interest, we then, at the end of the second year, we're now going to take the value of the account at the end of the first year, so the $10,300, and increase that by 3%. Okay, so we can see that in the second year, the increase was $309, whereas in the first year, the increase was $300, okay? And so we've compounded the interest, because in the second year, we've calculated interest on the interest, okay? Which is why we've increased by a bit more in the second year. In the third year, we'll increase by a bit more again. So what's that? Let me see if I can do that in my head. What's that? $318.27, I think. Sorry if that's not quite right. It's early morning. So we're increasing by $318.27. So again, it's going up by a little bit more in the third year. And that's because when we calculated the interest at the end of the third year, when we calculate the interest at the end of the third year, we've calculated 3% of the interest that was calculated that was added in the last 2 years. So it's not just 3% of the $10,000. So the whole idea of compound interest is that it's going to increase at a more and more rapid rate, and we're going to see, if we were to plot it as a graph, we're going to see that exponential growth happening. All right, so each year we're multiplying by 1.03. So calculate the value of the interest earned in the first year. Okay, actually, pretty much I just did that. So remember, the first year would be going from, we talked about an example like this yesterday too, where we did the change in during the fifth year. So during the first year, we'd be going from year 0 to year 1. Okay, that's the first year. So in this instance, that's going to be the interest in the first year. All right, let's say first year interest. Okay, at the end of the first year, it was worth $10,300. At the start of that year, it was worth $10,000, and so the interest is $300. Okay. Calculate the value of the interest earned in the second year. Okay, so the second year interest, it's going to be $10,609, so second year being from year 1 to year 2. Okay, so after at year 2, it's worth $10,609 minus what we were worth end of year 1, $10,300. So the interest we've earned there is $309. Calculate the value of the interest earned in the third year. Third year interest is going to be $10,927.27 minus $10,609. Just check my calculation this time. $10,927.27 minus 10,609. 31827. Good. My maths is holding up in the mornings. 31827. Okay, so explain why the interest earned each year is increasing, and that is because we are earning interest on previously earned interest. Not just on the principal amount. So when we talk about loans, we talk about the principal amount being the initial, or investments as well, being the initial amount borrowed or invested. Okay, so we're not just calculating 3% of the $10,000, we're calculating 3% of any interest that's been earned prior to then as well, which is why the interest earned each year is going up and up and up. V is the value of the investment after n years. Write down a rule connecting V and n. Okay, so again, we did a bit of this yesterday. So what we're seeing here is we're multiplying by 1.03 each year. Okay, so at year 1, we've multiplied our principal amount by 1.03. At year 2, we've multiplied our principal amount by 1.03 twice, so times 1.03 squared. At year 3, we've multiplied our principal amount by 0.03 3 times, so 0.03 cubed. So in this instance, our rule is going to be $10,000, our principal $10,000. We've multiplied that by 1.03 n times, if it's been n years. Use our rule to calculate the value of the investment after 10 years. Okay, so again, we could define a function. We talked about that yesterday. I'm only going to do 2 questions with this, so I might just go with it as it is. So in this case, when n equals 10, we're looking at V will be 10,000 times 1.03 to the power of 10. Now again, if you called that V of n in part E, you can just write down V of 10 and then write the answer down from your calculator straight away. So 10,000 times 1.03 to the power of 10. Okay, now again, let's be careful about the rounding on our calculator. We might adjust the setting for this exercise because we're probably going to deal with some large money amounts, but I'm not confident that that is... now, money, the default would be we give our answer to the nearest cent, so that is 2 decimal places. So I'm going to scroll up. I can only see 1 at the moment, so I'm going to hit enter and paste it down here so I can see to 2 decimal places. Great. So this is $13,439.16. Okay, use your rule to calculate how many years it will take for the value of the investment to double. Okay, and again, the wording here is a little vague. We had a question like this yesterday. I'm reading this as how many years, so to the nearest, to a whole number of years, and we need the investment to have doubled. So we need to think a little bit about that rounding at the end. So the initial investment was $10,000, so the investment will have doubled when the value is $20,000. Okay, so we need $20,000 equals $10,000 times 1.03 to the power of n. Then we're going to solve that for n. Okay, so again, if you define V of n, you can write down V of n equals 20,000 and put that in your calculator. So Control Delete to clear that. We're now going to solve menu 3.1. 20,000 equals 10,000 times 1.03 to the power of n. Get out of the power, comma n. Okay, so we're solving an exponential equation here. We've got the unknown in the power. Alright, so N is approximately 23.45 years. Okay, so again, we can check, but the investment won't have doubled after 23 years because it doesn't double until about 23.5 years, and so it will double after 24 years. So we have at least double the principal, double the investment, after, what did I say, 24 years. Okay, question 2. $10,000 is invested with interest paid at 3% per annum compounded monthly. Everything about this question is exactly the same as the previous question, except now we're going to compound the interest monthly. You'll note that the interest rate is still given per annum, so that's a per year interest rate. We'll always be given the interest rate for a loan or an investment as a per annum rate, and if we want to compound the interest more frequently than that, we need to make some adjustment to that. So we're going to compound the interest every month, so in 1 year we'll have done 12 compounds. So thinking about what's happening with compound interest, obviously, if we've compounded the interest 12 times, we're going to be growing it quicker, okay? Because we're calculating interest on interest more frequently, and so the investment overall will grow more quickly. The more frequently you compound the interest, the quicker the interest will grow. We'll see that throughout this question. Let's have a look. So we want to calculate the monthly interest rate, okay? So if 3% is the annual interest rate or the yearly interest rate, the monthly interest rate is going to be 3% divided by 12, which is 0.25%. Hence, calculate the amount of interest paid at the end of the first month. Okay, so let's just talk about this for a minute. So if we're going to have a 0.25% increase, that means we're going to have 100.25% of what we started with, okay, of the initial, which means we're multiplying by, so percent, remember, means per 100, divide by 100. So if we divide that number by 100, 1.0025, okay. There is a formula for working that out. I present that on the next page. The formula is to do 1 plus r over 100. So in this instance, 1 plus 0.25 over 100, over 100, which is 1 plus 0.0025, so we get 1.0025, okay? So you can use a formula, but in all honesty, it really is a very logical step. I want you to try and think through the logic of it. If I'm increasing something by 0.25%, I'm ending up with 100.25% of what I started with, and so converting that to a decimal, dividing by 100 is 1.0025. Okay, so interest paid at the end of the first month. So after 1 month, we're going to be taking our initial $10,000, multiplying it by 1.0025. Okay, so let's see what we get. Okay, $10,000 and $10,025. Okay, so we make $25 interest in the first month. Calculate the value of the investment after 1 month. Oh, sorry, I jumped ahead. This is our answer to part B. My apologies. That's the value of the investment after 1 month. If we wanted to just calculate the interest at the end of the first month, we would just be doing, sorry, not 2.5, 0.25%. So that's the interest of $10,000, which would be 0.0025 times 10,000, which is just the $25. Okay, so then adding that on tells us that at the end of 1 month we have $10,025. Calculate the value of the investment after 2 months. So now we're going to take, my apologies, we're going to take our $10,025 and again increase that by 0.25%. So multiply it by 1.0025. So multiply by 1.0025. And again, let's just check that rounding. So scroll up. Yep, okay. So we've got $10,050.06. If V is the value of the investment after n months, write down the rule connecting V and n. Okay, so again, thinking about the other way we could have done after 2 months was to think about, well, we've got our initial 10,000 and we're going to increase it by 0.25% twice. Okay, so same logic applies in an ongoing capacity. The value is the $10,000 multiplied by 1.0025, so increasing by 0.25% n times. Okay, so there's our rule. Alright, this time maybe I'll define my function, so I'm going to call it v of n. It's the value in terms of n, the number of years. I'm going to, and actually we might adjust the setting in our CAS, seeing as we're working with these money problems and we're constantly having this rounding problem because we're only seeing 6 digits and we need 7 to get to the nearest cent with this kind of level of money. So to adjust the setting, I'm going to click on the battery icon. I'm going to go to document settings and I'm going to change it from float 6 maybe just to float 8. Okay, that should be enough I think for now. Alright, so now let me just have a quick look. If I did that same calculation I did again, I would now see 8 digits, and so I'm not getting that rounding issue that I had before. Okay, I'm going to define my function in this case, just to refresh our memories on that. So menu 11, v of n, okay, we need to use function notation, equals 10,000 multiplied by 1.0025 to the power of n. Okay, so there's our rule, so now we can use it. Use your rule to calculate the value of the investment after 10 years. So that is to let n equal 10. So v of 10. We want to find what v is. So v of 10, the value after 10 years is, let's type it in here, v of 10. Okay, we're going to have, sorry, not 10 years, 10 months. That's an interesting question then. Let's be careful here. So this isn't right. So it's not n equals 10. Let's be careful about that because n is in months, okay? And so if we want 10 years, that's 120 months, which means that n equals 120. So we want v of 120 here. Okay, so the value after 120 months is $13,493.54 to the nearest cent. After how many months will the value of the investment have doubled? Okay, so this time v of n equals 20,000. Okay, remembering we need to write down an equation if we're solving it. So menu 3.1, solving v of n equals 20,000 for n. Alright, and we find that that's after 277.61 months. Okay. So to the nearest month, or not to the nearest month even, but after that means that after, because we don't compound the interest in the middle of the month, we can't just give the answer as 277.61 months or whatever. It will either be 277 or 278. Now if we round down to 277, our investment won't yet be at $20,000, so we need to round up. Okay, so therefore it is after 278 months. Sorry. Let's just have a quick look out of interest. So 278, if I divide that by 12, that'll tell me how many years. Oh, Control Enter. So that's just over 23 years to double. And so let's have a look at what happened in the previous example. So when we were compounding annually, so we should find that after 10 years, when we compounded the money annually, we had $13,439.16. Here we've got $13,493.54. So it's not an enormous difference. We're not talking about a really long time. And we're not talking about a very big interest rate, and we're not talking about a very big principal amount. But if you think about if you had $50,000 or $100,000 to invest, we get quite a big difference quite quickly. So this was about $13,400 and about $40, whereas this was $13,400 and just over $90. So an extra kind of $50 or so in the pocket by compounding monthly. If we look at how long it takes for the investment to double, when we were compounding annually, it took 24 years to double the investment. This is just over 23 years. Okay, so it's all happening a bit quicker. We're earning more and more interest because we're compounding the interest more frequently. So over a 10-year period, what is the difference between annual and monthly compounding? Okay, so our annual compounding amount was 1343916. So it was 13439.16. Sorry, that's the smaller one. So I'll subtract that from my monthly compounding amount. So my monthly one was 13493.54. So if we subtract them, we're going to be able to work out the difference. Now again, in our calcs, we want to get used to working nice and exactly. So we should have these two numbers sitting up here. There's that first number, minus, let's go and find the other one. There it is. Okay, so we get an extra $54.37. Is it quicker to double your money using monthly or yearly compounding? It's quicker to use it monthly. It's 23.1 years versus 24 years. Or you could make it in months. 24 years in months is 288, so it's 278 months versus 288 months. Okay. Alright, so that idea that the more frequently we compound, the quicker our investment grows, or the other way, if it's a loan, the more frequently the bank is compounding the interest, the quicker our loan amount is growing, and so therefore the quicker we need to be able to repay it. Okay, let's just have a look at a couple of slightly different problems before we finish up. So in a compound interest problem, we have four quantities: the principal amount that we invest, the number of interest-bearing or compounding periods. Okay, so if we're compounding annually for 10 years, that would be 10. If we're compounding monthly for 10 years, that would be 120. So the number of times you're going to compound your interest over the period of the loan or investment. Capital R is the annual interest rate, and lowercase r is the interest rate per interest-bearing period or compounding period. So again, if we had our annual interest rate was 3%, okay, then our monthly interest rate, lowercase r, would be the annual interest rate, uppercase R, so 3 divided by 12. Okay, we did that in our previous example. And using these four quantities, we get the formula that is for compounding interest, but again, I want you to try not to get too bogged down in formula. So the value of the investment after n interest-bearing or compounding periods is given by this. So it's our principal amount multiplied by, now I showed you this little 1 plus r over 100 rule before. That's really just how you get your, we call it the multiplying factor. So when we had an increase of 3% per annum, our multiplying factor was 1.03. Okay, so that would be simply, what this formula is doing. So if you can do that in your head, you don't need to use the formula. When we had our monthly interest rate of 0.25%, our multiplying factor per month was 1.0025. Okay, so yes, you can use the formula, but you also don't always need it, particularly for that number in the bracket there. So we've got the principal value multiplied by that multiplying factor, and then to the power of n, so the number of compounding periods. Okay, so what that means is we now have a rule that connects these four different quantities. Okay, well, sorry, yeah, these four different quantities. And so if we know any three of those quantities, we can work out the fourth one. Okay, so let's have a look at these examples. An investment account pays interest at a rate of 4.5% per annum. Okay, so that's our capital R, annual interest rate, compounding monthly. Okay, that's important. So we're going to need to work out what lowercase r is. So lowercase r is going to be uppercase R divided by 12 in this instance. So 4.5 on 12. Okay, so that is 0.375. 0.375% is our monthly interest rate. The amount of money invested, an amount of money is invested, and after 5 years, okay, its value is $8,000. Okay, so the final value is $8,000. The amount of money, we want to find the amount that was invested. So we want to find P. P is what we don't know. Okay. Now, 5 years at monthly compounding. Okay, so 5 years is 5 times 12, 60 months. Okay, so that means N is 60. Okay, so we've got the quantities we need for our formula. V is 8,000, lowercase r is 0.375, n is 60, and it's p that we don't know. So we can put our information into our formula. V equals, sorry, we know what V is. V is 8,000. 8,000 equals p times 1 plus 0.375 over 100 to the power of n. Now again, that number inside the bracket, if you prefer to think about that yourself, it's an increase of 0.375%, so 100.375%. So we're going to be multiplying by 1.00375 power of n. Okay. Either way, sorry, we know what n is. So n is 60, power of 60. Okay, so we can solve our equation. So menu 3.1, we're solving 8,000 equals an unknown value, p times, you can type x if you want, 1.00375, you can type that ugly expression with the fraction if you prefer, to the power of 60, and we want to solve for p. Okay, so our principal amount that we invested to the nearest cent, the question tells us, was $6,390.82 to the nearest cent. Okay, if 7,500 is invested, okay, so that's P, which the interest is compounded annually, okay, determine the annual interest rate, okay, so we want to know what our interest rate is, correct to 2 decimal places. So given that our annual, the interest rate is annual, both capital R and lowercase r are the same in this case, sorry, that we're compounding annually. The annual interest rate is the interest rate per compounding period. We want to calculate the interest rate. We'll give it to 2 decimal places. If the value of the investment grows to $10,000 in 6 years. Okay, so that's V. And 6 years compounding annually, so our N is in years, so N is 6. P was the 7,500. Okay, so we know the value is 10,000. And principal 7,500 multiplied by 1 plus r on 100. Now this is where we do need the formula, okay, because it's r that we're trying to find. You can do it another way. I'll show you in the CADs how we do it another way, but if I set up my formula and solve for r, so menu 3.1, 10,000 equals 7,500 multiplied by bracket 1 plus control divide for a fraction, 1 over, oh not 1, sorry, r over 100, and then it is to the power of 6. And we are solving for r. Control enter. Okay, so obviously r is our interest and interest rates. We can't have a negative interest rate, so it's the second number there, and we want to 2 decimal places, so r is 4.91% per annum. So you'll often see that PA, meaning per annum, per year. Okay, the other way you could have done that is a bit quicker to solve, to enter in your CAS. You could solve 10,000 equals 7,500 and just times, we'll just call it x for here, x to the power of 6, okay, and solve that for x. Sorry, control enter. Again, ignoring the negative one, we can see that x is 1.04911. So if we can make that conversion back from 1.04911 is 104.91%, so it's an increase of 4.91. You could just solve it that way as well. Alright, last example. If $2,000 is invested, so that's our principal amount, in an account in which interest is compounded weekly, let's be careful about that, determine the annual interest rate. Okay, so again, we want to know what capital R is. Because we are compounding weekly, there's 52 weeks in a year, so we know that capital R is lowercase r divided by 52. I'm just going to focus on working out what lowercase r is first, and then we'll work out what that means for the annual interest rate. The investment is worth $2,500, so that's the value after 3 years, so that's n. Oh, n's not that. So 3 years is, we want to work that out, so that's 3 times 52, so that's 106 weeks. Sorry, that's 2 times 50. What am I doing? 156 weeks. Okay. And so n is 156. Okay, so we've got our value, $2,500, is equal to our principal, which was 2,000, multiplied by 1 plus r over 100 to the power of n, which in this case is 156. Okay, we're going to solve for r. We want 2 decimal places. 31. Although we want 2 decimal places for uppercase r, so let's just be careful about this. We don't want to round too much too early. Never round. There's no reason to round with your CAS. So 2,500 equals 2,000 times 1 plus r on 100. Oh, sorry, don't want the bracket there, we want it there. To the power of, what are we doing, 156. And we want to solve for r. Sorry, control enter. Okay, so r is about 0.1431, okay, percent. So that is the weekly rate. Okay, which means that the annual rate is going to be, sorry, I wrote this rule up here around the wrong way. Sorry, the weekly rate is the annual rate divided by 52, okay, which means that the annual rate is the weekly rate multiplied by 52. So if my weekly rate is 0.14%, my annual rate is going to be 52 times that. Okay, so there's no reason to round with my CAS. I'm going to type in, I don't need to type in lots of decimal places. I could copy and paste, but it gets complicated with all those, in fact there's 2 solutions and r equals and the word or. If I copy this down, it gets hard to use that number. So I'm just going to save myself some energy. I'm just going to do 52. I'm going to multiply it by, I'm going to write more than 2 decimal places, but I'm not going to write heaps. So 0.14, 314309. I'll just type in what I can see there. Okay, so that is 7.44% to 2 decimal places. Just out of interest, I don't know whether it would have an effect, but let me just have a quick look. Yeah, now see, if I had rounded the weekly rate to 2 decimal places and then multiplied by 52, I get a very different answer. So it's really important that you don't round off your answer until the very end when you're being told to give a rounded answer. So I kept that weekly rate of 0.14314% to as many decimal places as I could see, and then multiplying that by 52, I'm keeping a much more accurate answer for my annual rate. If you had rounded your weekly rate to 2 decimal places and then multiplied by 52, you would have the wrong answer. Okay, so it's really important not to round too early in your questions. Okay, so you've got the list of work for today. Again, in any questions where it asks you to use trial and error, your book was designed not to have a CAS, and so you want to actually use your CAS to solve when the question says trial and error. Okay, good luck.